And we're live. Welcome to the Evidence Reasons Academy. I'm Salvador Cordova. Happy Thanksgiving to everyone. Much to be happy and thankful for this holiday season. I'm joined by Vlad for the first time. He's been a recent addition to our YouTube channel family, and I'm very grateful. He's taken an interest in my work. The Evidence Reasons Academy channel is not very well visited. I'm glad when I can get 20 views. Ironically, some of my other stuff, like on Denver KLTT radio, has already gotten somewhere in the range of like 30,000 views for some of my videos just on YouTube alone. That's not including the podcast and the live listens on the radio station. So I'd estimate even the 5 shows I've done between the live radio audience and YouTube and podcasts, there's probably between, say, 100,000 to 200,000 views total on my 5 shows. So that just totally dwarfs probably a whole several months of views on the Evidence Reasons Academy. I've gotten a lot of views on my main channel, Evidence and Reasons. So the Academy, we go really deep into the nuts and bolts. It's not meant so much to entertain a broad audience. I just kind of dump thoughts on there, and sometimes it's useful, sometimes it's not. And it just gives me the freedom to just let people know I'm still breathing and making content. And sometimes the really scientific, technical stuff is done on this channel. It's for specialized audience. And then sometimes we just deviate into topics. And then some days we just shoot the breeze, like today. So Vlad has been saying kind things about my work, and he's been asking a lot of questions. And I said, this is a great opportunity to, if I could just get him on YouTube, it's easier for me to answer them live, and I don't have to type. It's easier for me just to talk than to type. So greetings, everyone, and happy Thanksgiving, Jungle Jargon. Thank you. So, Vlad, tell the audience anything you'd like me and the audience to know about you and why you're interested in my work.
Oh, it's nothing so special about me. I have an interest as a hobby in learning certain things about biology and cosmology, things like that. And I just found your channel is pretty valuable.
How long ago when was the first time you saw my channel?
I've been following it somewhat regularly for, I'd say, about a year now.
And how did you find it? Through a Google search or?
It might have been. I'm not sure. I think I heard your name was mentioned on a web form somewhere, perhaps, and I ended up finding you on YouTube.
Well, that's great. Well, I'm appreciative of that. So you had a bunch of questions for me. And one thing I'm finding, honestly, sometimes the question also, however you put forward a question, can actually, sometimes I might have to correct it and say, this is a better question to ask. So I'll give you one example, because I thought about this. You're asking about the definition of evolution in terms of allele changes. They say evolution is allele changes over time. And that's actually a very poor way of even framing, because there's a lot of changes that are not alleles or allele frequencies, at least not in the traditional sense. So a gene has a lot of variants, and those variants are called alleles. So for example, like hair or skin color, there'll be, it's still at the same location of the gene, but it could be slightly varied, between individuals. So we have locations in our genome where that gene exists, and then each individual might have a variation in that location, and that's an allele. The problem is we're finding out that genes aren't everything. We also have things called regulatory elements that tell you how much of something to make. So even if two people have identical genes, they might have different regulatory apparatus. And beyond that, there's a lot that's inherited that is not directly a result of genes, like the glycome. I mean, this is like really relatively new discoveries. And so
Right.
this gene-centric viewpoint is a little bit becoming a little bit archaic, and it's going to continue to be. But so much evolutionary literature was written because of the. So we first had Darwinism, just pure Darwinism, before they even understood the notion of inheritance. And then we had Mendelian. Gregor Mendel figured out a lot of the mechanisms, some of the mechanisms of inheritance in terms of genes, this famous experiment with peas. But then, so that merged together in what they called neo-Darwinism, which was, I don't know when, like the 20s, 1920s, 1930s. It was at its peak in the 1950s, and it became contentious. At this point, some evolutionary biologists say neo-Darwinism is gone. So there's a huge amount of evolutionary literature that is so gene-centric, and it's really kind of funny. I'm just like, there's a lot that doesn't involve genes. In fact, our genome has huge amounts of non-genetic, non-gene-based information, and is so you'll hear the term non-coding DNA. There's like 98% of the genome's non-coding, and we're still, there's contentious debates how important that those non-coding regions are. So we built all this evolutionary biology on genes, and that's only 2% of the problem as far as the genome. We're not even talking about the glycome, the lipidome, the interactome, and so many other terms. So I just wanted to, that was one question you posed in the comment section, and I was like, okay, we have to kind of really expand your horizons here of what needs to be dealt with. And I think that we might keep that definition as a reference just to say how bad evolutionary biology is. It's so stuck in old thinking.
Right.
So, okay, fire away. If you have other questions, I'll try my best to answer them. I'm not saying that I'll be right, but we'll give it a shot.
Oh, geez. They have a one thing atheists bring up, evolutionists bring up a lot also is when you talk about how life began, they say, well, evolution has nothing to do with biogenesis. But isn't the idea of universal common ancestry based on the likelihood of certain events that would have needed to occur before life began in order for life to begin? Okay. If you understand what I mean.
Yes. So this is how I deal with that problem. I'll say, so, all right, what I try to do as best as I can is, all right, this is a debate. By the way, evolutionary biology is driven a lot by clever rhetoric, and some of it's not very honest, and misdirection. It's not really based a lot on science. So they would love to get into arguments over definitions. I saw one exchange between Michael Behe and Dr. Dan Stern-Cardinal, and 45 minutes were spent on arguing definitions.
Definitions.
Huh?
Yeah, this point has been brought up before. I think you were talking about this on your last show, that terms in biology aren't always well defined.
Evolutionary biology in particular.
Evolutionary biology.
So the way to get around this is if I were arguing with an atheist, I wouldn't even argue. I'll say, okay, so evolution doesn't solve the problem of abiogenesis. That's what I would say. So you're telling me that it doesn't solve the problem of abiogenesis. So you can't say evolution has solved the mystery of life because abiogenesis is critical to life.
Right.
So I'll say, okay, you settle it. That's the way I do it. I say, hey, look, you're claiming all the complexity of life is explained by evolution. Then I'll say, well, isn't it true? You all say that evolution doesn't deal with abiogenesis. So there's a whole field out there of complexity that evolution doesn't solve. Is that right?
Right.
That's
Right.
how I would deal with it. And then you can talk about abiogenesis. You'll say, okay, evolution doesn't solve all these problems. I'm going to list them all. So like the origin of, there's like this book, The Stairway of Life, or anything that James Tour has done. I'll say, okay, so it doesn't solve the first, it doesn't solve how we have homolinkage in the DNAs. It doesn't solve the polymerization, um, of proteins. And there's just any number of things. It doesn't solve how the genetic code originated mechanically. You can't even, how does it solve the emergence of of the cell membrane? I mean, the laundry list is enormous. How
Right.
does
There's inherited information also in the that gets passed down apart from genes. There's also information inherited in the cell membrane.
yes, and the glycome, and we call so
Glycome.
the cell membrane inheritance is, they sometimes call that structural inheritance. And see,
Okay.
all these. I wish I had more time to actually investigate it just for my own information. But I'll give you a very interesting example. Gary Felsenfeld, is a very respected scientist. He wrote a book on, or an essay on epigenetics. That means inherit, stuff that's beyond the gene. It's
Right.
a terrible term now. It's gotten so. Um, it's gotten, anyway. In that essay, he talked about a paramecium. It has a cilia. They surgically modified it, and all the descendants were okay. It would rotate one way, like clockwise or counterclockwise. Surgically modified it. All the descendants had it rotate the other way. It was incredible.
Huh.
So that had nothing to do with genes. Oh, someone asked this. Yes, I'm still a young Earth creationist, and it does matter to me. I don't think that it is on a scientific ground. Is I could not argue it as well as I'd like to, and I think over time we'll be able to um, um, God will provide the evidence we need. We're not quite there, and I wish young Earth creationists would not be leading with some of the arguments they have because they're so weak. Um, the strongest arguments are in protein biology, cellular biology, prokaryote, eukaryote transition, and origin of life. We just start building up from there. Um, I see a lot of people that are just totally unqualified, spouting their nonsense, representing young Earth creationism, and they're terrible. It's an embarrassment. So um, I have no hesitation criticizing young Earth creationists when they make bad arguments because they make us all look bad. And
Yeah, Kent Hovind was just in another debate, and he did poorly, I think, as he.
yeah. I mean, let me point out something. Oh, by the way, I didn't mean to interrupt you, Vlad. Go ahead. You saw Kent Hovind.
Yeah, he was on a debate just the other day, and I just thought he did poorly.
Oh, I expect he does. Some people, he has a big fan club, and that fan club is not composed of very good scientists.
Right.
So that's so anyway. I had to entertain Jungle Jargon's question. So we asked about abiogenesis, and then we talked a little bit about structural inheritance. There's so many forms of inheritance. So I talked about the paramecium. Um, there are a few. It's very difficult to do experiments in structural inheritance, but I think eventually we'll get there. We do know the glycome, which is the sugar code. So you have the genetic code. That's very well known. A lot of people don't know about the sugar code, and part of the problem is we haven't even figured out even a fraction of this sugar code.
What do they do to how do they figure out the function that the certain codes result in?
Okay, so
how did you research this? How do they
okay, it was
figure things out?
sure. This is so for the genetic code. This was miserably difficult research. They just knew we had DNA and we had proteins. We didn't quite know how they related to each other. And the guy who figured it out, Marshall Nierenberg, he had some really clever experiments. I mean, uh, it, it's almost painful to describe the experiments. But let me show you the genetic code. And this was years in development to uncover this. I'm going to share my screen so you could see it. I'd like to find one that actually has it in terms. A lot of them are stated in RNA code, which is a little harder. So let me just see if I could. Give me a moment here so I could call this up. It's a bit of a pain. So before we go there, are you familiar? Can you tell me what? I'm just asking this so I get a feel for where you are. Do you know the alphabet of DNA?
CTGA.
Okay, good. And the alphabet for amino acids is roughly the English alphabet.
Okay.
It's not exactly. Can I show off a little bit here?
Yeah, of course.
Okay, let me try to do this by memory. Actually, I shouldn't use my cheat sheet. Let me turn this down, and let's see if I can remember. Okay, so there are 20 canonical amino acids and 2 kind of rare ones. So you get up to 22. And then we have some combinations of amino acids. So I'm going to try to go through the alphabet of amino acids. So, okay, so for DNA, the nucleic acids, A is for adenine, C is for cytosine, G is for guanine, T is for thymine, U is for uracil. Those are the nucleic acids. U is the R. We don't have to go there. Visit that later. So for amino acids, you also have A. A is for alanine. B is for, oh, now I'm stuck. Immediately, B is for, I think, asparagine or aspartic acid / aspartate. C is for cysteine. D is for aspartic acid / aspartate. E is for glutamic acid / glutamate. F is for phenylalanine. G is for glycine. H is for histidine. I is for isoleucine. J is for leucine or isoleucine. K is for lysine. L is for leucine. M is for methionine. N is for asparagine. O is for seleno. It's either pyrrolysine. I think it's pyrrolysine. I could be wrong. P is for proline. Q is for glutamine, R is for arginine, S is for serine, T is for threonine, U is for selenocysteine, V is for valine, W is tryptophan, X is any, Y is for tyrosine, and Z is for glutamine or glutamic acid slash glutamate. I probably blew a couple of them. So you have,
Oh,
so just for the readers, let me see. I'm going to bring this up because I'm a little upset with myself. I used to know this so well, but if you want to find out what the alphabet is, FASTA. There is this thing called FASTA format, and I'll just show it on my screen. And this is, I wish all the arguments that people, all the wasted energy that they spend on the fossil record, it's like you could just spend just a few, maybe 5 minutes just looking at the alphabet. So, by the way, congratulations to you. You understood ACTG is the DNA alphabet. That's so. Let me see how I totally may have botched this up. All right. So, what did I say? B is aspartic acid or asparagine. And then see what there was one I kind of missed. It's pyrolysine.
lysine.
And then U is selenocysteine. I got that right. And Z is glutamic acid, glutamine. So I was close. All right. So you see here they have the basic English alphabet, and then for DNA you have the ACGT: adenine, cytosine, guanine, thymine, and then for RNA you have uracil. There's some rare combinations. We don't have to get into that. So you're at okay. I'm trying to go back to your question. How did we figure this out? So what happened was they had to make some really clever experiments where they'd break the DNA and then they'd compare it with the change in an amino acid or something like that. These are really painstaking. I mean, this is back in the day. It's so hard to synthesize DNA. We can do it much easier now. But man, that was difficult. So a lot of the way we learn is by breaking things and seeing what else breaks.
Right.
So so this is I hope you could see it. So this is the genetic code.
Mm-hmm.
And so you heard me like arginine and serine and lysine and isoleucine and methionine, alanine. So A is for alanine in an amino acid, but the way you spell it in terms of DNA, there are 4 ways you could do it. GCT, which is guanine, cytosine, thymine, or guanine, cytosine, or guanine, cytosine, adenine, or guanine, cytosine, guanine. So there's some amino acids that have multiple ways to spell it in terms of DNA. And so this is the genetic code and how it translates to a amino acid. And here's, so there are 2 representations of how. So just call out an amino acid. Just if you get it wrong, I'll help you. Think of an amino acid. And if you don't, just look at this table and just say, look at this, and I'll help you. So just look at the little wheel here.
Okay. What can I? Is it cytosine? Something like that?
Okay, it would, let me look here. I think cysteine. Okay, this is where it's confusing. Cysteine is an amino acid. Cytosine is a nucleic acid. So cytosine is spelled cytosine. I mean, cysteine the letter is C, cysteine, and it's spelled G. Let me see, G U C. Let me look here. GTC, cysteine, TGT, and I don't know why it's not spelling it. TGT. I don't know why the wheel is not, I'm not reading this wheel correctly. TGT, TGC. Okay, TGT, TGC. Okay, unfortunately, this is the RNA code. This is the RNA code of U. When you have T's, it's DNA. You can convert the T to a U. Okay. It took me a while to figure out how to read this. So T, 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 T. Okay, so I'll know better next time how to do this. All right, so just call out another amino acid, and I'll spell it for you.
Well, there's GLN. What is that?
That's glutamine.
Glutamine.
So that is spelled.
Could be CAG or CAA. Is that right?
CAG. Wait, CAA or CAG. And then we can also look at this table. Let's see, look for glutamine.
Where is it?
Where's glutamine? It should be GLN, CAA and CAG. Very good.
Okay.
So you could see how the DNA, we call that a triplet. It can correspond to an amino acid or what they call a stop codon. There's a punctuation called stop. So you can then, let me see, I'm going to just take this down. This was actually a good way to, you asked how they figured this out. Like I said, if you play with the DNA and you keep changing the letters, you can see what amino acid it makes. And to actually do that experimentally is pretty miserable. They just change this DNA and say, oh, look, and you could see with just a process of elimination.
Right. And so do they go and look and see if the protein or the amino acid is just no longer there, or do they look for a loss of function somewhere in the organism?
Well, okay. My understanding is when you change the DNA, you can actually detect a corresponding change in an amino acid.
Right.
Okay. And so, but I have to emphasize this is miserably difficult to do. But I mean, you could think conceptually, if you know this piece of DNA changes this protein, and you change one letter of the DNA and see the effect it has.
And do you think that's limited in some way with what we're able to discover from that?
There are always in biology, there are always exceptions to the rule. But in general, we have a good handle on the genetic code. There are some problems in the translation process that may yield funny results. So it's not 100% accurate. And there's discussion as to why that is. It could be just sometimes the chemistry just doesn't quite work accurately as we would, there's an idealization. So there are mistakes that are made in the translation process that will give you kind of funny results. So I'd say 99% of the time that genetic code is correct.
Okay.
It's pretty good. There are always exceptions, and it's been a while since I've looked at some of those exceptions. So now what happens is a protein is made of amino acids. So you could see then if you have Okay, so you need 3 DNA letters to make one amino acid. So if you have a protein that is 1200, a protein that's 400 amino acids long, you'll need 1200 DNA letters to create it, because you need 3 DNA letters per amino acid to spell it.
Right.
And so I wanted to show a graphic here, DNA to protein. See if I have a picture here. Uh, I wanted to show one that's. There's some pictures that are better than others. Oh, well, why don't I? I'll try this one. Let me try this one. I should get a collection of a collection of graphics that I really like to help teach. So let me bring this back up. So here is a snippet of a protein here.
Okay.
Thionine, proline. I don't know what GIN is. Funny. I presume that's glutamine, serine, valine, histidine, alanine, leucine, methionine, cysteine. I think that's a misspelling. It should be GLN.
GLN, huh?
Yeah, I think that should be glutamine. Yeah, CAA is glutamine, and we know that. Okay, let's just check. CAA.
CAA is glutamine.
Yeah,
Right.
it's glutamine. CAA is glutamine. So you have CAA goes to glutamine. All right, so we confirmed that. So if you have a protein that is 400 amino acids long, you'll need 3 times as many DNA letters. So that would be 400 times 3, which is 1,200. So when they say about a mutation, so if you change the letter here, let's say, I'll go with this. Let's go with the first one, ATG. ATG. Just randomly, why don't you misspell one of the letters for me of ATG? Just pick one.
We'll say ACG instead of ATG.
Okay, let's see what happens. ACG. So we have ACG, and it says here that would be threonine. Let me just verify that. Where are you, threonine?
There it is. It's second row, third one down. The second column, sorry.
Oh, here it is, third row. ACT. So you're saying you go from ATG to ACG?
Yeah.
Okay, let's see. ACG, there you go. Becomes a threonine.
Uh-huh.
So that is an example of the effect of a mutation. And I'll tell you what's a really devastating one. They're punctuation marks called stop codons. That means this is where the protein, it's saying, hey, this is where you stop translating. And what's really bad, it's very easy to make a stop codon. So you could, one mutation can truncate an entire protein.
Right.
And just blow it out of the water. What we call it, a point mutation. It's even worse what we call insertion and deletion mutations. And I'm just like, this is like getting a sentence and then it, and you put the period like at the beginning of the sentence. It just kills it. You can shut down an entire protein with one mutation.
So when they're talking about reverse RNA transcription. How does that work?
Okay.
Is that
Yes, it happens, and I'll show it to you. Let's see. Central dogma of molecular. There are various ways, and let me see if I could see where I could find you an example here. Central dogma.
is when that happens? Is that changing a letter also?
Okay, hang on. Let me see. Okay, I found one diagram that talks about what you were asking about. So we could. This is the so-called central dogma of molecular biology.
Uh-huh.
So a simplified way of saying that is DNA is transcribed to RNA. We could call it messenger RNA.
Messenger RNA. Okay.
And messenger RNA is translated to a protein. There are a few times that the DNA can be modified by if you have an mRNA floating around inside the cell, it can actually change the DNA. That doesn't happen very often. Definitely, though, you don't have like a protein going back to the DNA. This is a very rare pathway.
Uh-huh.
That doesn't, most of the changes in DNA are, at least as far as evolutionary theory, are just accidents in the copy process. But we do have to say there are a few times you have a reverse transcription. So when you hear about, let me make sure I got this right, reverse transcription, transposon. Let me see if this is correct. Okay, so you've heard about junk DNA, and a lot of the so-called junk DNA are retrotransposons, where these RNAs that are floating around end up being shoved into the DNA. You know, they get reverse transcribed
Uh-huh.
DNA. So this can cause severe birth defects, and what they unfortunately what the evolutionists said, well, we see some examples of reverse transcription, so therefore anytime we see this particular section of DNA that just happens to look like it's reverse transcription, they say it was. They don't like the idea that it was specially created for that purpose. And so the creationists will say, hey, it's not as easy as you, it's not as cut and dry as you're saying. So you'll hear that term because they'll say, I think, let me see, fraction of the genome. Hang on, fraction of genome retro. I just Googled here. So let me show you what I Googled so it's not a mystery to you or the audience. I just Googled what fraction of the genome are retrotransposons. And they say it is about a third of the human genome. And let me find something out. I'll just show you the spelling of it because it's
That
better.
sounds like a lot.
It is. Okay, so let's see, retro. So allus are, I don't know if I should know this. Okay, I'm seeing the word allu and retrotransposon. So I'll give you how this relates to the evolution debate while you hear this. They'll say so much, like you said, it seems like that's a lot, right? They'll
Yeah.
say 10% of the human genomes are made of allu elements. And I'll show you what the allu spelling, I'll show it to you. Just so we're not, you can actually see this, allu spelling. Let's see if I could find it. Allu sequence. It's going to be a little miserable here.
Now, it's a way. How do they tell this from a mutation? How do they
Okay.
determine whether or not something's been reverse transcribed or if it's been
Was it created or intelligently designed? See, this
yeah.
is a good question. All right. So what they say, well, look, it looks like all these copies, and we see them. We do see them in, we do see them like from like a parent to a child. You will
Mm-hmm,
see the child may have an extra copy, and that
mm-hmm,
definitely that's a reverse transcription.
mm-hmm.
So that is what we call a structural mutation, structural variation.
Okay.
There's not a lot of words. A lot of the mutations in evolutionary biology are just single DNAs. When you have just wholesale duplications, they don't really have a word for that I know of. They just call it a duplication mutation. I'm trying to find the spelling of an ALU element here. See if I could, just so we're not, okay. I mean, I would just like so you could just see what it might look like in terms of the spelling. Okay, here's the spelling of an Alua. I'd like putting it up on the screen so we could just have a discussion
Yeah.
as to respond to your questions. So you have these. So when they see a sequence like this, now remember this is in, our genome has 3.3 gigabase pairs. Actually, it's more like 6.6. If you're going for what they call the haploid genome, 6.6 billion base pairs. And you'll find a sequence that looks like this. And
Okay.
oh, okay, that looks like an ALU because we have a template. And they'll see it repeated about 1,000,000 times, that sequence. This sequence you'll see repeated 1,000,000 times in the genome. And so they'll say, well, since we see that these duplicate between parent and child, they reason falsely that all of the 1,000,000 copies were just insertions, reverse transcriptions, and it was just proliferating by accident and it's junk. The problem with that reasoning is we're finding that the positioning and the role of that is really important. And I did a show on that on Real Science Radio. So if you look, have you worked a little bit in IT, or are you familiar with some IT concepts like a server farm? A server farm?
Good. Yeah.
Yeah, great. So if you look at a server farm, all the servers are almost identical.
Right.
So an evolutionary biologist, by comparison, he'll say, look at all the duplicates. They must be junk because they're
This
identical.
must not be doing anything. Yeah.
I'm just like baloney. I mean, you look at a server farm, all the servers are identical, but they serve a purpose.
Yeah.
And it turns out that this is a little bit sophisticated. When the DNA is transcribed to an RNA for an ALU element, that ALU element can be modified. It serves as a memory element, a local memory element, and it can also it can adopt various conformations, what they call like the zDNA conformation. The normal conformation is B, but when it goes into the zDNA conformation, it's like a switch. So that spelling helps it to switch one way or the other, and that's what they call a flip-on. And I try to share this with evolutionary biologists, and they're like, "No, I don't believe it." I'm just like, "Look, there's experimental evidence for this. You guys just are unwilling to learn." And I said, "Look, I could show you that this results in creating all this extra memory inside the cell that is dynamic. It's like zeros and ones. And if anyone's doubting me, let me see if I could dig up the reference. ALU element. Oh, why don't I just show this? ALU binary code Herbert. So an ALU is a retrotransposon, and they said these were all reverse transcribed and it's junk. And then this paper here talks about binary codes. It creates a binary code. It is extremely this is a painful read. Oh my goodness. I was reading this on this channel or another one. I read the entire. I was only through half the paper, and this thing was so difficult to wade through to describe how this actually works.
Wow.
But I mean, this is not a trivial paper. And so when you talk to an evolutionary biologist, they'll never reference a paper like this because they're stuck in their ways that this is junk. It's not functional. It doesn't do anything. And then I keep saying, look, I have a paper right here by the Royal Society. I had an evolutionary biologist come on one of my channels. And he said, I don't really believe this, he's only one author and, they would have discovered. I'm just like, dude, we have more confirmation for this than any of your theories because this is actual experimental evidence. And he would just have nothing to do with it. I was just laughing. I said, talk about willful blindness. I showed the paper, I showed the experiments, and he would just like disregard it. I don't believe it. I'm like, okay, suit yourself.
Man.
Yeah. So when you get in these debates, so talk about the ALU elements. What I would recommend is you just shove this paper in their face.
Okay.
You more, okay? I could show you more. So that's where reverse transcription comes in. They're talking about, look at all the junk. I'm just like, you guys don't even have a clue. There's even more stuff with that we're learning, like we call phase separation. So my experience when I talk with evolutionary biologists, they're going to expect you to go at it with one angle. But if you're up to date on the literature, you're going to run circles around them. And that was actually part of my job, is to research what sort of, I didn't actually have to do the experiments, thank God. I just had to look and see what literature had come up. I will tell you this. Some of this has only happened like in the last 15 years.
Right.
So the pace of this, of discovery, and some of the stuff that I will reference when I argue with evolutionists is only like in the last 3 years.
Mm-hmm.
It's moving so fast, and the creationist arguments are actually, unlike guys, even the creationist arguments are like 30, 40 years old. I'm just like, you really need to update where you are. And that's why I'm appreciative you're watching my channel, because you'll get to learn some of the updated arguments.
Yeah, for sure. Recently, Aaron Robb mentions just gave a couple examples of speciation on his web channel, and he'll show like two different lizards, and they'll be lizards on one side of a mountain, and they migrate to another side of the mountain, and then he does a video and says, look, they can't breed anymore because they're a new species now, but they're still lizards, and they often say, yeah, well, it's because of genetic drift. They can no longer reproduce with each other, but they never mention any specific genetic criteria they use to determine whether or not they can't really reproduce with each other anymore, or
right.
Or why.
Okay, this is where I say again, don't fight on the terms of. Are you ever fascinated by military history?
Sure.
Oh, great. There's a saying, don't fight on the enemy's ground of their choosing. Make them fight on the ground of your choosing, if you can.
Right.
And historically, some battles were definitely won because, an overconfident opponent just said, I'll beat him wherever he wants to fight. And of course, like the infamous or famous battle of Agincourt, the English were outnumbered anywhere from like 6-1, 10-1, but they chose their field of battle very carefully. And the French came in and they were just funneled into this killing zone. I shouldn't laugh but I like, they would have been, the English being outnumbered 10-1, if they were out in the open field, they would have been wiped out.
Right.
But instead they wiped out the French. They defeated an opponent that was 10 times larger, and they had very few casualties. The English did. The French were just mauled. So why did I bring that up? I have said creationists need to dump this argument. Did it speciate or not? I'll tell you, there's two reasons why. One, no one agrees what a species is.
Yeah.
Even evolutionary biologists will not agree what a species is. So why even start on something so amorphous? Second, that's not the real problem for evolution. So the real problem is the origin of complexity. So
Right.
even Darwin's book, The Origin of Species by Means of Natural Selection, or the Preservation of Favored Races in the Struggle for Existence, something like that, it's really the central problem that it tried to solve really was in chapter 6, organs of extreme perfection and complication. So Darwin was not a very good writer. His English, his prose is just awful to read. Can't hardly understand what he's saying half the time. But the evolutionists want you to get into a debate about speciation, and I avoid it. I say the real issue is, where do you have new major protein families? Major protein families. And let me see if I have, oh my goodness. I don't know if you've watched this one. Let me see if you, I have this video here. I did it on Denver KLTT. I gave it a cute, all right, they have their title for it. I gave it my title. And mine is Aaron Ross Sewage Flushed Down the Toilet on Denver KLTT. And I point out, and this is on my channel somewhere. Let's see if I could find it. There was a Satanist, and Aaron Ra was. Let me see if I can. I'm sorry, I need to stop this. Okay, let me see if I could find. I hope I could find it. Oh, there it is. That's a quote. Okay, hang on. Let me show it to you. Now he made a rebuttal video, which I didn't even bother watching because the guy's an idiot.
Yeah.
So this is what he said: proteins don't have an effing common ancestor. And he doesn't realize that's very problematic for evolutionary biology. Because, so I would encourage you to watch that video if you haven't. So the issue is not species. The issue is major protein families. And it's not too hard. Let me just see if I could find some pictures here. So if you look at the parts, oh yeah, let's see. Okay. So I like this picture here, the parts of the part.
Because if there's no mutation going on, then it's not evolution. It's just complexity.
Well, I would encourage you to watch this video, because let me see if I could find it. Well, unfortunately, the graphics were a little bit messed up, but I have some other better graphics. Let me see if I could find one with a better graphic. Um, since we have talked about amino acids and proteins, and I was pretty upset at Steve McRae. He always wants to pick on the worst creationists. He never wanted to engage the better ones like me. If I do say so.
Right.
I mean, I was mad. I'm just like, oh, I get it. You're gonna get the least qualified creationist, not bring on the one that could actually argue his case well, and you're gonna pit him against your best guy. I said, that's not very honest. I offered to argue my case, and he was just dismissive. I said, I'm not, I doubt I will ever want to deal with that guy again.
That's typical. They're always just want to attack the weakest argument,
Yeah. So let me show you this. This is a collagen protein. So remember, it has that pretty much the full English alphabet to spell
Right.
it. There's a very definite pattern here, and let me show it to you. It's that. Every third amino acid is a G over this stretch. It's a striking visual example. This is a very critical protein. You wouldn't have metazoans. Metazoans are animals that have embryos.
Right.
Not this protein, that doesn't happen. And this is not a trivial protein. It's not just this pattern. I could show you more complexity, but this is the way to recognize it. Sometimes I could actually look at a protein sequence and I'll say, oh my goodness, that's a collagen.
Is that collagen? It's collagen.
Right. So collagen, you'll see it in beauty products, in health food stores to make your skin look beautiful or whatever. It is a real protein.
It's like fat or something, isn't it?
No, it is a protein, collagen.
Yeah.
All right. So that's you see that distinctive pattern, right? That's collagen.
Yeah.
There's another protein, and this is called a zinc finger protein. And but it also has a distinctive pattern. You can't see it here. That the red is a C for cysteine, and H is for histidine. And you could see this regular pattern here. And the point of this is why Aaron Ross Sewage said there's no ancestor for all proteins. And Daniel Stern Cardinal had to agree, because there's no transitional. You can't form. It doesn't make sense to say what's the ancestor of these two proteins.
Well, don't proteins need a living organism to reproduce?
Yes.
Then how do they evolve?
Okay, so what the evolutionists will say, is that the first cell didn't have that many proteins. It just had the bare minimum needed to survive. So a bacteria does not have a collagen or a zinc finger. Humans have collagen and they have zinc finger proteins.
Right.
So what they'll say is that, after you get the first cell, it just keeps mutating the DNA and you'll end up creating a collagen or a zinc finger or both. And so what I said, okay, do you ever even think about how difficult it is to make something as complicated as a collagen that actually works? Or how about a zinc finger? And what they realize is that you can't have a common ancestor gene / protein that you can modify in gradual steps that will have a descendant that is both a collagen and a zinc finger. They're just so radically different.
Right.
So then, and I had this famous video here, and I really have to credit Dr. Dan. Do you know about Dr. Dan?
Yeah, I've seen a couple of your debates with him.
Okay, so first off, my first two debates was 4 years ago. I felt I held my own, but I think if I debated him again, it would be a different story because a lot has been discovered, and I kind of know what his arguments are, and I think I would win that one hands down, honestly. Let me see. I wanted to show you something. Let's see. Okay, let me play this. See if I could get this. Okay, hang on. Let me reshare this. Just give me 1 second. I'm going to reshare this. Share screen. I don't know if the audio will come through well. I'll try my best. I'll tell you what he had to say if you couldn't hear it. So,
that proteins don't share universal common ancestry. We disagree about cellular life, but we agree that proteins don't share universal common ancestry.
so he said, we disagree about cellular life, but we agree proteins don't share universal common ancestry. That in his view, different regions of the genome just had to spontaneously become one protein, and another part becomes spontaneously another over time. And I'm just like, have evolutionary biologists even calculated the odds of forming something that is so well integrated?
No, they would never do that.
Of course not. They'll just say it's 100% true. Just like
Yeah, they'll say it's 100% because we know it happened.
Yeah.
Oh.
And see, again, there are rhetorical tricks there. So have you seen the videos of the topoisomerase enzyme?
No, not yet.
Okay, so what I would recommend is, for starters, the best video that deals with Aaron Raw is, and I'll send it to you in an email, but I'll also cite it here. Let me see.
Okay.
For the sake of the viewers. For the sake of the viewers, just go to the Evidence Reasons website, the main one. I mean, not website, YouTube channel. And you could search on sewage. I just call him Ross. I know that was mean.
Okay.
And the title of the video is Aaron Ross Sewage Gets Flushed Down the Toilet. But I'll put it here. Okay, it is now in the it's in the side chat, and I'm going to email you before I forget, because now that I know, now that I could see that you understand the genetic code. Oops, what did I do? Oh, I froze my system. Hang on.
Oh.
I need to do a restart.
Okay.
Let's see if I can recover from this. All right, we partially recovered. All right, so I'm going to write to you. So let me just. Okay, we recovered. Oh, this is live, Mark. Greetings. Happy Thanksgiving, Mark. Great seeing you. So now that, I mean, I'm really glad that you understand like the genetic code and then a protein. This should be really easy for you to get through this, and you'll because I liken it to like the parts of a car. It doesn't make sense to have a common ancestor for the parts. Like, what's the common ancestor, even conceptually? of a tire and a car battery.
Right.
You can take a tire and modify it in incremental steps, and it's still a tire.
Right.
Really, you have to do wholesale redoing to go from a tire to a gas tank. You don't really have a functional intermediate. It's either going to be you see, you can modify a tire and it'll still be a tire. But if you try to modify a tire to become a gas tank, it's going to be a very bad gas tank or a bad tire on the way. It just doesn't.
So there's no pathway for a protein to become a different protein.
Yeah, and different major you can modify the basic architecture and it'll still be that type. So in classification of proteins, we'll say, okay, this is a topoisomerase of a human. And there are variations of that even in the human genome. You have like topoisomerase 2 alpha and topoisomerase 2 beta. They're very similar, but they're still topoisomerases.
They're classified by their shape, aren't they?
They're classified by their shape and their sequence. So we have 4 levels of classification. Actually, really 2.5. So the sequence itself, we call that the primary structure. So when you saw the spelling, that's the primary structure.
Right, okay.
When you look at the 3D shape, it's what they call the tertiary and quaternary structure.
Okay. But
shape is good enough. I mean, just use, they like these fancy terms, and there are reasons for that. So there are.
It's gonna lose function, but from one shape to another shape. It's
exactly.
There's no pathway for it to maintain function between two. The shapes can only be so different.
Exactly. Okay. Just remember, proteins are actually, a lot of them are either structural parts or parts of a machine. So just like when you're building a machine, the parts have to fit together the right way and interact.
Oh, right. Okay.
This is also why it's very hard to have a random mutation do anything. You hope it doesn't affect the system radically. Okay, so I could go to a car and I could say, oh, let me make these modifications and it's going to run faster. But if you're doing a wholesale, like going from, a non-turbocharged to a turbocharged engine, you're going to have to do some redoing,
Right.
Or if you're even more radical, if you're going from, 4 cylinders to 8 cylinders, you're going to have to do a lot of overhaul. And at the biological level, you have so many things that need to physically fit together. The shapes have to be just like the parts of a car. They have to be complementary. So in the engine, you have the engine block that has holes in it where the cylinders can come in. You have to drill the hole just big enough for that cylinder to go in. You don't want it too tight or too loose. And same for how about any of the connections when you have nuts and bolts? You don't make the nut too small or too big. You have to make it just right. And so a lot of the parts of biology have to have that Goldilocks zone where they fit just right. And I'm just you evolutionary biologists, don't you ever take that into account? When you have a random mutation and it's changing the shape, that could be potentially very bad. You could shut down an entire system. And I could go on to all the sorts of mutations that'll totally shut down the system. So I'm just this is why. So like in a car, you can change some things and the car still runs, right? Like you could rip out the windshield wipers, and on a sunny day the car will still run. So there are a lot of mutational changes that superficially, depending on the environment you're running it in, it may not look like it has any effect at all until say you run that car on a rainy day and its windshield wipers aren't working, or same for the defroster. So in a protein, there are probably parts that could be dispensed with and it'll survive in a particular context. But then if you stress it out in another context, that change could actually be pretty important. And then also, you could make changes that totally alter the shape of the protein so radically that it stops working. This is like totally physically breaking apart, you know. And this is why I enjoy teaching this sort of stuff, because this is a lot more fun than the fossil record, making arguments over the fossil record.
Yeah,
Yeah.
yeah. For me, it's a lot more interesting, anyways.
Yeah. So the topoisomerase. So I think you'll see in that air and raw sewage flushed down the toilet.
Uh-huh.
You'll see the topoisomerase. I'll give a description of the topoisomerase enzyme.
Yeah, I'll have to check that out.
I'd say that's one of the better videos. There are anything that I did for Denver KLTT. So I think if you just search on the Evidence Reasons channel, not the Evidence Reasons Academy channel, I have 2 YouTube channels.
Uh-huh.
Anything with KLTT, you'll get some good content, very succinct arguments. And one thing you'll probably notice, they don't make a lot of debunked videos on my appearances.
Right. Well, that's cool, man.
Yeah. So do you have other questions before we wrap it up? This doesn't have to be the last time we talk. Maybe after you watch some of my videos, you can come back.
I have a lot of questions.
Sure.
But I appreciate you taking the time. And like I said, I really enjoy your material and your 2 YouTube channels. And I like the point you made the other day about, this was something I never heard before, the point you made about compression and error fixing.
Yeah, the Shannon-Noisy channel coding theorem.
Yeah.
So the evolutionists, thank you very much. I think that was really important, because these evolutionary biologists say, well, the designer's so incompetent because if he had built cells right, there wouldn't be errors to correct. I'm just like, you guys are so clueless. I said, you don't know anything about information theory. You would totally know that if the goal were compactness, you would allow plenty of errors to come in and you correct them on the fly. That's what we do in communication systems. The internet is driven by that. The modems that connect, like your computer to to someone else's computer. Error correction. That's how you can get so much more speed in the internet, because you're able to compact the data, send it through with lots of errors, and then it's corrected on the other end. And there are all sorts of, oh my goodness, it's not Reed-Solomon, all sorts of error correction schemes for internet. It's just unbelievable. I don't even know the names. It's been like 30 years since I've studied coding theory and error correction. So they probably have new stuff there that I definitely don't know. It's very, very sophisticated. I'm appreciative you noticed that, because evolutionists are so quick to say anytime there's an error, they say that's an incompetent designer. I said no.
Right. Yeah. Well, that's really cool, man.
Yeah. Well, maybe we'll talk again sometime. I had a lot of fun. We're at an hour in about 15 minutes. So hopefully this isn't goodbye. I'm interested in having these discussions because I'm trying to create an intelligent design creation science course. And you've shown me the importance of teaching the central dogma of molecular biology, which we covered a little bit today. I mean, it didn't take long for you to see the genetic code laid out. You were able to say, okay, what's this DNA triplet? And you said, okay, that's the amino acid. Or you take the amino acid and you figure out the DNA sequence. I said, that's great. I will tell you, this is what gets me very upset. There are people that have been debating creation evolution. They wouldn't be able to do what you just did today. And I'm like,
well, I've been following like I said, I've been following you somewhat regularly for a good year at least.
Yeah,
so I've learned a thing or two.
Well, I'm going to be a little bit more. I'm going to be trying to release a website that will probably take people through sequentially, a little bit more structured, because my YouTube channels are a little bit of an editing room floor. They're all rough drafts of ideas. It's not
Right.
the final product. Although my appearances on Denver KLTT radio, so it was, I would make like an appearance for an hour. It would take 2 days to write the script and then 2 days of editing. So that's 4 days, and it involved 4 people.
Right.
It takes a lot to get a polished product out. Of course, these are my most highly watched videos. And then I'm in a documentary about the church that has like 2 million views now.
Mm-hmm.
But that was 9 months of filming and 9 months of editing and a pretty big budget. Thankfully, I didn't have to pay for it. But and that had nothing to do with intelligent design, but that's probably like my most watched is the documentary. Oh, speaking of which, audience, I was in the documentary, The Real David Platt. So visit therealdavidplatt.com if you're at all curious. And let me just, maybe I'll put some comments in the comment section for people that are interested. So I'm eventually hoping I'll have this a little bit more structured and, to take someone in a self-study course. There's some people that barely even know what atoms are, and I'll have to maybe make modules to help people like that. You're off to a good start because you already understand the genetic code.
Oh, good.
What you did today, it's like, I wish I would say 95%, 99% of the audiences that hear me, especially the atheist morons on modern day debate, would not even understand that. I had a debate opponent who didn't even, I'm just like, dude, you're so out of your league. You're talking, you saw that with me and Carissa.
I saw, yeah, and what was that guy's name? Max? I think he was.
He said, I'm not a scientist. I'm just like, well, look, you're talking to 2 scientists here, and our specialty happens to be in biology and stuff. I'm just like, dude,
yeah,
you're clueless.
So I'm smart enough to appreciate the time, and like I said, I think you're one of my favorite creation scientists.
Oh, thank you. Thank you. I thank you for the kind words for Carissa. She is a professor of biology.
Yeah,
she's a former evolutionary biologist. I mean, her official title is marine biologist, but she said she's pretty much virtually an evolutionary biologist, and she became a creationist. So, having her as a debate partner, and our opponent is just like so clueless. I'm just like, you don't know who you're dealing with, He's just laughing his head off and just like, dude, your brain's fried with drugs or something, because he was so out of his depth. So anyway, I'd like to thank the audience. We're going to wrap this up, but hopefully this isn't goodbye. It's just till we meet again. Happy Thanksgiving, happy holidays. I am praying I'll be able to continue to do more content throughout my channels. I will delve into things that may seem disconnected, just like the McLean Bible Church thing and David Platt. And I'd say Christian apologetics, the science, the intelligent design, creation science, evolution controversy is only one component of Christian apologetics. The other part is archaeology, which I cover very, very little. I wish I could do more. Christian testimony, and then cultural observation. So you see pieces of that in my various channels. I recently talked about Jordan Peterson, who was just, I think, just very insightful about the effects, as people reject the Christian faith, its effect on society has been very profound.
Mm-hmm.
So you'll see a variety of things on my channel. That's just who I am. Occasionally, I'll just throw stuff out just for fun. But anyway, Vlad, I'll give you the last word, and then we'll wrap it up.
Like I said, I really appreciate the time. You're really one of my favorite creation scientists. I would love to talk to you whenever you have the time. I hope you keep putting out new material, and yeah, and it's nice for someone. It's a good resource for a layman like myself to learn something.
Well, it's been a pleasure. I'll meet you backstage for just a minute. I'm going to end the stream, but just hang on there, Vlad, and we'll talk a little bit afterward.